In this example, we're going to be solving for acceleration. So here's the situation. A train that is initially traveling at 19.4 meters per second south accelerates uniformly until it's traveling at 16.8 meters per second north. The magnitude of the displacement during this interval is 36.7 meters. Determine the acceleration of the train. Now the tricky thing about this is you're not given information about the direction of the displacement. You are told that it's just north-south movement. So we've got south, north. It doesn't matter at all which direction you choose to be positive or negative. We know that initially, at some initial position, we don't actually know where that initial position is, but let's say snapshot 1, we're just taking a picture of the car initially. It's traveling to the south with some initial velocity. And then sometime later, some next snapshot, it's traveling north at v2. But we don't actually know whether or not the train has a net northward displacement between point 1 and point 2, or if it has a net southward displacement between point 1 and point 2. All we're told is that the magnitude of the displacement is 36.7 meters. But before we choose a kinematics equation and try to substitute in any variables that we know, we're going to need to figure out what the direction of the overall displacement is. And here's one way to visualize that. We can go back to looking at a velocity time graph, since we're only really told information about the velocity at our 2 points. Initially, we're told that the train is traveling at 19.4 meters per second south. So this is north, this is velocity, and this is south, which is our negative direction. So initially, the train is traveling at negative 19.4 meters per second. Those are our units for this graph. This is our time axis, south. At some time later, time 2, the train is traveling at v2, 16.8 meters per second north. So it doesn't have quite the same magnitude as the magnitude of the original velocity. So this is 16.8 meters per second north. Because we know this is a problem that involves constant acceleration, we can connect those 2 points with a straight line. That's what the velocity time graph will look like. We also learned an important thing when we talked about velocity time graphs. We learned that we can figure out the displacement between 2 points in a constant acceleration continuous motion problem by figuring out the area under the velocity time graph. If we just look at the area without even determining what the area is, you can easily tell that the displacement in the negative direction is larger in magnitude than the displacement in the positive direction. And you can tell that because the magnitude of the train's velocity in the southward direction is larger than the magnitude of the train's velocity in the northward direction later on. So this graph is telling you that the direction of the overall displacement between point 1 and point 2 is negative. Therefore, we can state, that the displacement is negative 36.7 meters, which means 36.7 meters south. Now we have enough information to choose a kinematics equation to use. V1 we know is negative 19.4 meters per second. That's in the southward direction. V2 is 16.8 meters per second, so that's northward. And we now just figured out that the direction of the displacement is southward. So that means that our displacement is negative 36.7 meters. And we were asked to find the acceleration. So when we select our kinematics equation, we're going to want to use one that involves all of these variables. So that means we're going to choose this one. v2 squared equals v1 squared plus 2 times acceleration times displacement. And we're going to want to solve for acceleration. So if I rearrange, that's v2 squared minus v1 squared over 2 delta d equals acceleration. Now I'll just substitute in my numbers. v2 squared was 16.8 squared. v1 squared was negative 19.4 squared. But when I square a negative number, it becomes positive. So I'll keep that in mind. And my displacement is negative 36.7 meters. When I evaluate this, keeping in mind that I'm dealing with 3 significant figures in this case, I'm going to get an acceleration of 1.28229 meters per second squared. I'm dealing with 3 significant figures, so I'm going to want to round that to 1.28 meters per second squared. If I look back to my original question, I can ask myself, does it make sense that the car is accelerating in the northward direction? Yes, because originally it was going south, it slowed down, it stopped, and then it started going northward and accelerating northward. If I look at my velocity time graph, does it make sense that the acceleration is positive? Yes, because the slope of that line is positive. So that's a good double check. So now I'll go to my final statement. Therefore, the acceleration of the train was 1.28 meters per second squared north.